To start this video, we're going to review how to simplify irrational numbers either to the correct number of significant figures or to simplify it to an exact answer. Remember, back in Module 1, Learning Objective 2, we looked at exponents and radicals. And in this last section, we talked about how to find the exact value of irrational numbers with circles, circumference, and area. Now we're going to look at 4 different examples. The first one that we have here is the square root of 168. If we want to find the approximate answer, we're going to use a calculator. And remember, we're going to be using the Casio, Fraction, FX, 260 solar ones. That's what's allowed for our HiSET test. So we're going to type in 168, shift, and then press the x squared button. That'll give us the square root. And our calculator comes up with 12.9614814. Remember, even though the calculator stops at that decimal place, it's still going to go on forever. On the test, it'll probably tell you which place to round to, but if we're not given that, we need to go with the number of significant figures. And the number of significant figures we start with is 3. So we're going to round this to 3 significant figures, which puts us at the 9. Since 6 is greater than 5, this becomes 13.0 for an approximate value. We're going to do the same thing with the square root of 88. We're going to type this into the calculator, 88, shifts, x squared, and we get 9.38083152. We have 2 numbers here, so we want 2 significant figures. That puts us at 9. For examples 3 and 4. 12 shift x squared gives us 3.46, but we have 2 values that we start with, so we're going to make this 3.5. And finally, for example 4, 224 shift square root. We need another 3 significant figures, so this is 15.0 because the 10th place has a 9 and the value after that is a 6. Now that's how we would find an approximate answer using significant figures. But what if we wanted to know the exact answer? Remember, the exact answer is a simplified version of this that we use prime factorization to find, but we don't round it. We just leave it as some number times the square root of another number. First thing we're going to do right off the top is see if we can divide by 2. 168 divided by 2 gives me 84. If I break that into 2, I get 2 and 42. 2 and 21, 3 and 7. So then I'm going to write this out as the square root of 2 times the square root of 2 times the square root of 2 times the square root of 3 times the square root of 7. I'm going to put any of my pairs together. Those ones don't have a pair. So this is 2 times the square root of 2 times 3 times 7. So this is 2 square root of 42. Probably wondering how I was able to go from square root of 2 times square root of 2 to the whole number of 2. Anytime we have a number times itself, like has an exponent of 1, so we can add those exponents. So this is the square root of 2 squared. A square and a square root are opposite of each other, so they would cancel each other out. Let's look at 88. This would give us 2 and 44. Divide that again. We could go 4 and 11. The reason I chose to do that is because 4 is a perfect square. So this is 2 square root of 22. If that was too much of a jump, this is 2 and 2. So these two give me this. 11 and 2 are unpaired. So 2 times 11 gives me 22. For the square root of 12, this is 3 and 4. We just saw that 4 was a perfect square. This is 2 square root of 3. For 224, that gets us 7 and 8. 8 is 4 and 2. So I'm going to write this one out. So we have the square root of 4, square root of 2, square root of 2, square root of 2, square root of 7, square root of 8. Square root of 4 is 2. We have another 2 here. 2, 7, and 8 are unpaired. 2 times 2 is 4. 2 times 7 times 8 gives us 112. So these examples were for the exact solution rather than looking at an approximate value. Now that we reviewed that, let's look at how these will play a role in solving problems with the Pythagorean theorem. Example 1. Find the exact length of x. Go ahead and pause the video, take a brief break, and try to solve this on your own. Since we want to find the exact length of x, that tells me that we don't want to approximate our value. Because our right angle is here, one of these is A, one of these is B, but this long side here is going to be C. X squared plus 38 squared will be equal to 50 squared. I don't want to work with very big numbers, so I'm going to be doing some things here that might seem confusing, but I'm going to justify them with the algebraic principles. First, I'm going to subtract 38 squared from both sides. That leaves me with x squared equal to 50 squared minus 38 squared. When I take 50 squared and I subtract 38 squared, I get 1056. Now I can square root 1056. That's kind of a big one, so I'm going to see if I divide by 4 first, and it does. That gives me the square root of 4, the square root of 264. Might as well see if that's divisible by 4. Just so happens to be. We know that this is going to be 6 and 11, 2 and 3. We have a pair of 4 and 4. We have 2, 3, and 11 left over. 4 times 4 is 16. Square root of 66. If we were looking for the exact answer. And most of the time we wouldn't. We would want to know what this is and an approximate value, especially if we had to measure and cut something for that length of A. So let's do that. Let's look at an example where we have to round to the correct number of significant figures. For example 2, we need to find the diagonal length of a square with an area of 81 centimeters squared. So if 81 centimeters squared, that's our area. We know that these two lengths are going to be congruent because it's a square. It's by definition that way. So if I take this as a square root, it gets me 9 centimeters. So each one of these is going to be 9. 9 squared plus 9 squared is going to be equal to the distance squared. 81 plus 81 equals d squared. Oops. Should be 162. Let's just double check. And d squared square root is 12.72792206. But here's the thing. What's the correct number of significant figures? That might seem like a challenge, but we know the values up to this point right here are exact. I would say go 3 significant figures. This distance here is approximately 12.7 centimeters. But triangles and squares and rectangles, those aren't the only places that we are going to see the Pythagorean theorem being used. We can also use it to find the distance on a coordinate plane. All we need to know is the 2 coordinate points we need to find the distance between. We're going to draw a quick sketch. -2, +2. I'm just going to call this one A, and this one B. It's probably going to get confusing. So where's the triangle? Right here. So the x value is 5. This is -2. Over here, we have 2 and 4. 4 minus 2 gives me 2, so my height here is 2. And to go from -2 to 5 is 7. And then I want to find C. One thing we haven't talked about yet is a shortcut. To save yourself a little bit of work, square root both sides right at the start. That gives you 2 squared plus 7 squared. You're going to take the square root of that, and that will equal C. That gives me 4 plus 49, which is 53. Doesn't really have anything that can be divided by, so we leave it because that's the exact distance between these two, the square root of 53. Now we've looked at 3 different ways that the Pythagorean theorem might be used, or the types of questions you might see. There is one last problem I want you to try on your own. Find the lengths of A and B to the correct significant figures.